In this video, we're going to talk about simplifying algebraic operations, specifically using function notation, the operations, as well as new operations like composition and finding inverses. So we're going to start with the order of operations. You probably learned this previously as PEMDAS. The problem with that algorithm or that set of instructions is that the P is misleading. It assumes that you're only going to encounter parentheses, but you can encounter all kinds of grouping symbols. So the grouping symbols could include parentheses, brackets, or other quantities, but it also includes substitution of a variable or an entire expression, since substitution includes a grouping symbol, meaning if you were to substitute 5 in for x, it technically should have a parentheses around it when you substitute it. The second step is to evaluate exponents and logarithms from left to right. You might have just heard this word for the first time called a logarithm. A logarithm is the inverse operation of an exponent. So we'll learn more about logarithms later in the year. Okay, so this step would also include square roots and cube roots, because a cube root and a square root are actually an exponent, which we'll also learn about more later in the year. The third step is multiplication and division from left to right. This step includes something called modulus. Modulus is the remainder when you divide. You will need that at times during this year, but also a lot during a code class or a class about programming. The fourth and last step is to do addition and subtraction from left to right. All right, let's take a look at some of these using the function notation. So function notation is a way to describe equations with a better and more longer lasting notation than using y's and x's. Y's and x's are limited to the xy plane, but function notation allows us to describe real-world scenarios, for instance, like velocity and time. This would be read v of t in that scenario, and this sentence will make more sense. It would be, if this were v of t, it would be the function of velocity with respect to time, or time changing the velocity. So for the sake of this page of notes, anything in blue is what we're doing in English, but what we're doing in green is everything that we're doing mathematically, the universal language. So f of x is the function of f with respect to x. Math is asking me to produce and output a dependent variable based on an independent variable. Keep in mind, dependent means changes with the thing that doesn't change, independent. So in that example I mentioned earlier, velocity is changing with respect to time because we have no way to change time. So you might say, well, what's the big deal? Well, take a look at this. If I were to talk about something we formerly known as slope, and slope, you might have had a teacher that actually described slope as rate of change, because it's actually what slope is. Slope is kind of like an easier way to say rate of change. It is a ratio between a change in one input value relative to a one output value corresponding to the input values of that. So in Algebra 1, you had y2 minus y1 over x2 minus x1. But in this world of function notation, it becomes f of b, b meaning second value, minus f of a, meaning first value, divided by b minus a. And we'll take a look at that so you can see how this function notation is changing things we already learned from Algebra 1, just using a more universal language. Imagine this again was velocity and time. It would be velocity at the second time minus velocity at the first time minus those two times. And that makes more sense than trying to describe velocity using y and time using x, which doesn't make sense in that situation. All right, so let's take a look at some other operations. So operations you're used to seeing, like addition, subtraction, and multiplication, the way that they change in function notation is they simply will say f plus g. And your job is to know what f and g are, and so that would be read as the sum of f and g. And this will require you to combine like terms. So the easiest operation to have to deal with is addition, because all you're doing is take the like terms of f and the like terms of g and adding them together. However, any operation other than addition will require the use of a parentheses. The grouping symbol allows you to properly use the operation that it is attached to, the function that's attached to, and then properly combine like terms after it. So f minus g, the difference of f and g, it requires first distributing a negative sign, that negative sign, to all the terms in g. So everything in g will become negative. Then you will combine like terms. Notice a lot of times in my notes, I simply abbreviate combining like terms as CLT. So the product of f and g could use a solid dot, or it could use nothing. It could just be FG. And it's assumed that you know when you see FG that it means multiplication. It's the only time you'll see two terms right next to each other like that. Think about when you have a term like 3x. So if you have a term like 3x, it's actually 3 times x, but we don't write 3.x. So this is read as the product of f and g, and this will require either distributing f or foiling f and g and then combining like terms once you've done the multiplication. Okay, so the last one is division, and division is always, even when you learned about it as a child in elementary school, division is always one of those operations that takes a little more time. So all of these operations will involve parentheses. This one you put a parentheses to distribute, these you have parentheses to FOIL. This one the parentheses comes from factoring. So when you do the quotient of f and g, in order to evaluate this, you have to factor out a common factor, a GCF, which is what you've always done. You just weren't taught that way as a child. But if you were to divide something, what you're really doing is grouping it into equal groups, and those equal groups are a common factor. Now in algebra, this is going to create something called a domain restriction because denominators cannot equal 0. And you find them by setting the denominator not equal to 0 and solving for x. And I will refer back to this when we see it in the examples. Okay, so the next operation that's new to us is something called composition. And composition is not, it's new to us in terms of its name, but we've seen it before because f composed with g, which is how this is read. The other way to write it is f of g with a parentheses here. That little open circle means composed. This is not read fog, this is read f of g, and this is also read f of g, or f composed with g. It requires substituting all of g of x into the x's of f, meaning we're going to substitute g into f, just like we did in Algebra 1 when we were doing solving systems of equations, and we had substitution, and we had graphing, and we had elimination. Well, this is the substitution method. I wish it was called the composition method, but Algebra 1 textbooks use substitution method. And the last operation we need to find is something called the inverse of a function. The inverse of a function is denoted with a little -1 on the function. It's not an exponent. It looks like an exponent of -1, but it actually is denoted inverse. The inverse, it is read the inverse of f of x. Algebraically, this is when the domain is replaced with the range, and the range is replaced with the domain. However, what does it require me to do? It actually requires me to switch the input and output values. So I take the x and make it a y, I take the y and make it an x, and then I solve for the new input value.